Hello, my name is Sherbin Niley, and today we're going to go over this question from the Oxford PAT workbook. The question's premise goes as follows. A fishbowl of height 4r/3 is formed by removing the top third of a sphere of radius r. The fishbowl is fixed in the sand so that the rim is parallel with the ground. A small marble of mass m rests at the bottom of the fishbowl. Assuming all surfaces are frictionless and ignoring air resistance, find the maximum initial velocity that could be given to the marble for it to land back in the fishbowl. So again, it's given this initial velocity of v0, and we're trying to figure out at what point, or what is the maximum v0 can be such that it falls in the fishbowl and doesn't go, over. And I highly recommend trying this out for yourself. I do think it's a very interesting problem, and I do think that its solution can be very insightful. What we can do is we can actually kind of split this up into two problems. So let's consider what happens when the ball is right here, right? Whenever the ball is here, it has another velocity, a velocity that's speed, that's magnitude, is less than the initial, but still that's the velocity we want to be looking at. So let's call that v1. And we want a v1 at this point such that it does not overshoot this rim right here. In fact, we want the edge case because we're looking for the maximum initial velocity, right? So we want the maximum v1 can be so that it ends up inside the fishbowl, which would be hitting this rim right here, which would be traversing this distance right here in such a way that it falls down to exactly the same elevation that it was before. And why am I considering this velocity instead of the initial velocity? Because, well, if we think about it, we can solve for this v1 in terms of v0 just with energy considerations, right? We can use an energy consideration to solve for the magnitude of v1. And so what do we do from here, right? Well, we can use the kinematics approach to find out the maximum v1 can be. So let's start that. Let's start by figuring out what this horizontal distance is here. So, remember, this right here, this distance right here, vertical one, that's going to be equal to r/3. How do we know that? Well, this is equal to r, right? This is r, and this total is 4r/3. So then this has to be r/3, meaning that we can use that to solve for this angle right here, which I will color in orange, theta. So we can say that it would be cosine of theta is equal to r/3r, right? Or if I want to be, it's r/3 over r, or again, simplified, it's just going to be r/3r, or 1/3. So then, what do we do with this? Well, let's think about what we can do with that. Well, let's think about how we can use this in the equation. Well, we can find out, we can use this to find out what this distance is right here, this x distance, which again, I'm just going to call this x, right? And this x distance is going to be, well, sine of theta is equal to x over r, therefore r times sine theta is going to be equal to x. So what is sine theta? Well, if we know this is equal to cosine theta, we can use the Pythagorean identity and say 1 minus cosine theta squared is equal to sine theta squared, which means that 1 minus 1/9 is equal to sine theta squared, which means that what we're looking for, or our final answer for sine theta, is equal to radical 8 over 3. So r radical 8 over 3 is equal to x. And since this horizontal distance is actually 2x, what we are looking for, or let's say d, is equal to 2 radical 8 over 3. You can simplify this. You can draw out you can draw out a 2 from here. So I think it would become 2 times 2 times, you draw 4, yeah, it'll become this, or 4 radical 2 over 3. And don't forget that there's an r here, and there always will be. Okay, what now? What else can we do here? Well, we need to find out the components of the velocity vector right here. So we have v1, and we want to find out v1x and v1y, respectively. So how can we do that? Well, we know that this vector and this vector are perpendicular to each other, right? This is the v1 is the tangential velocity, so that means it has to be perpendicular to the radius vector. So we have our object right here at the end. We have the radius vector. We have the horizontal, to which we want to find the angle. And then we have this angle right here. And again, we want to find the angle of this, where this is perpendicular to that. So let's call this alpha, which would mean that 90 is equal to alpha plus some other angle. Let's say b, and b is what we're looking for. Well, 90 minus alpha would be equal to b, right? Based on this triangle right here, given that this is a right angle, that must be equal to theta. So b must be equal to theta. So b, in this case, is just equal to theta. Right here, this theta. What does that mean? Well, that means the vertical component of this is going to be sine theta v1, and the horizontal component is going to be cosine theta v1. So what can we do with this? Well, we can set up two kinematics equations and use that to solve for it. We know that it has to traverse this total distance of 4 times rad 2 over 3r. 4 times rad 2 over 3r in t time with that velocity right there, cosine theta v. So cosine theta v1. We also know that it must be at the exact same elevation. So delta y, which is equal to 0, is equal to the initial velocity, which is going to be sine theta t, or the initial velocity times time, minus 1/2 gt squared. And we can use that. We can use this one to find an expression for time, and then plug that in here to find an expression for v1 in terms of things that are not v1. And I forgot to mention that there's a v1 there. Oopsie daisy. So anyway, we have sine theta times, the t's would cross out in this case, but I guess I'll just write it out. Sine theta times t is equal to 1/2 gt squared. The t's cancel, so you're left with v1 times sine theta, which I'll remind you, sine theta is equal to radical 8 over 3. So radical 8 over 3 is equal to 1/2 gt squared. Oof, this is a strange interface. Now, again, we're just going to isolate this for, oh sorry, no, this is not, definitely not t squared, that's just t. And again, we're just going to isolate this for t. So t is equal to, okay, so it's just going to cut me off. T is equal to v1 times 2 times radical 8 over 3 all over g. And if we want to simplify this, it becomes 4 radical 2 over 3 times v1 over g. And that's our time. And then we can just plug that into this expression right here, which would give us 4 radical 2 over 3 times cosine, v1 over g times cosine of theta is, as we've already established, 1/3, 1 over 3, times v1, and that is equal to this expression over here. Well, in this case, this would just cancel out, right? Same thing going on here, same thing going on there. That just cancels out. So we're left with r times 3 times the g as well, because we're going to move that over to that side, times g is equal to v1 squared. And that is our expression for v1 in terms of r and g. What now? Well, we can use energy to find v1 in terms of v naught, right? Or the other way around. So we know that our initial energy is going to be equal to 1/2 mv squared, or mv naught squared, and we know our final energy is going to be equal to 1/2 mv1 squared plus mg, and our height is 4r over 3. Now let's get rid of all these m's, because we can. Right? We cross them out from all sides. We end up with this. And what we also know is that v1 squared is equal to 3rg. So this becomes 1/2 3rg plus 4 over 3rg is equal to 1/2 v naught squared. Finally, we can just multiply everything by 2. Or not finally, but we can just multiply everything by 2 to get that 3rg plus 4 over 3, or sorry, not 4, it would be 8 now. 8 over 3rg is equal to v naught squared, and it's not letting me go down anymore. You do this, you add these two together, that becomes 17rg over 3 is equal to v squared, and so, or v naught squared, so v naught is equal to 17 over 3rg. That is the magnitude of v naught, which would be our maximum initial velocity. And that right there is the solution to the problem.